The topic to be discussed in this video is counter type analog to digital converter or digital RAM analog to digital converter. This is the basic block diagram of counter type ADC. The components present in that counter type ADC are AND gate. This one is AND gate, binary counter, digital to analog converter. Here we use some flip-flop latch, which is used to store the digital data. And the last one is comparator. The components present in that counter type ADC are AND gate, binary counter, latch. Here we use some latch, which is used to, this one is latch, which is used to store the digital output, DAC, digital to analog converter, and comparator. The counter is here. This is the binary counter. The counter is reset to 0 count by the reset pulse. The reset pulse is, this is the reset pulse. That reset pulse is high. That means active condition. The binary counter is reset to 0. That means all are zeros. Upon the release of reset, upon the release of reset means reset inactive. Reset inactive means this is the duration in which the reset is inactive. The clock pulses are counted by the binary counter. These are the clock pulses. Are counted by the binary counter. Initially, the counter is reset to 0 count by the reset pulse. That means reset pulse is in active condition. Upon the release of reset means the reset in active condition, the clock pulses are counted by the binary counter. These are the clock pulses are applied to one input of the AND gate. These clock pulses go through the AND gate. These are the clock pulses go through the AND gate, which is enabled by the comparator. The AND gate is enabled by the comparator, whose output of the comparator is 1. The output of the AND gate is 1 into that clock pulse. The AND gate is allowed clock pulses when the comparator output is 1. These pulses go through that AND gate. These pulses, clock pulses, go through the AND gate, which is enabled by the comparator. This is the comparator whose output is high. This is the time. As time increases, the number of pulses count increases with time. The number of pulses count 1, 2, 3, 4, 5, 6, 7, 8. This is the 3-bit counter type analog to digital converter. That means 2 cube, that is equal to 8 clock pulses. For 8-bit, 8 clock pulses. The number of pulses count increases with the time shown in figure. Coming to DAC. DAC converts binary data to analog voltage VD. Digital to analog converter converts binary data. The binary data is came from output of the binary counter, which is applied to that input to the DAC. DAC converts this binary data into analog voltage. Analog voltage. This is the VD is the analog voltage of DAC compared with the analog input VA. Compared with analog input VA. Suppose if the analog input voltage is varies with time. Suppose this is the analog one sine wave varies with time. The analog input voltage is varies with time. Varies with time. First of all, this analog input signal is sampled using a sample and hold circuit. Using this analog signal is sampled using a sample and hold circuit. Sample and hold circuit. Sample and hold circuit. Before it is applied to that comparator. Before it is applied to that comparator. Suppose the analog input is vary in nature. That means with respect to time that values are changes. First we need to convert this analog signal into sampled version signal with the help of sample and hold circuit before applying to that comparator. That VA is applied to non-inverting terminal of the comparator. That means plus non-inverting terminal of the comparator. One input of that comparator is applied to positive terminal. That means non-inverting terminal of the comparator. That means one input is VA. Another input to that comparator is VD. That VD is from output of the DAC. That VD is from output of the DAC. The analog output VD of VD of DAC. The analog output. This is the analog voltage VD of a DAC. Of a DAC is compared to the analog input VA by the comparator. VA by the comparator. If VA, this is the VA. This is the VA. This is the VA means some sample value. Analog value. 16, 18, 19, 20, the value, some sample value. If VA is greater than VD, analog voltage value, that means output of the DAC. VA is greater than means VA is connected to plus terminal, VD is connected to minus terminal. VA is greater than VD means the output of the comparator is 1. The output of the comparator is 1. That means becomes high and the AND gate is enabled. This AND gate is enabled to allow the transmission of these clock pulses to the counter. To the counter. This is the case 1. Case 2. When VA is less than VD. When VA is less than VD means VD is at VD is connected to negative terminal of the comparator. VA is connected to positive terminal of the comparator. When VA is less than VD means the output of the comparator is 0. The output of the comparator becomes low, not high, and the AND gate is disabled. That means low means 0. That AND gate is disabled. This stops the counting. The binary counter stops the counting because this AND gate is disabled. When AND gate is disabled, when VA is less than VD. When VA is less than or equal to VD. This is the VA. This one is VD. This line straight. This line represents VA. At that instant, at the 8th clock pulse, this is the VD. VD is greater than VA. That means this is the VD. This is the VA. VD is greater than VA at 8 clock pulse. At that instant, the AND gate is disabled. The binary counter stops the count. Stops the counts. And the digital output of the counter represents at that instant the digital output of the counter. The digital output of the counter represents the analog input voltage VA. Analog input voltage VA. For new value of analog input VA, again for new value of that analog input value VA, a second reset pulse is applied. Up to this, the conversion is completed. For a 3-bit 2 cube, that means 8 clock pulses are needed for complete conversion. At the end of the 8 clock pulse, that means VD is greater than VA. The binary counter stops the count. Therefore, that particular VA, that sample value is sample value 1, is converted into digital output. For the second sample and hold value, again the counter need to be reset by using a second reset pulse. By using second reset pulse, this process is continuous until up to all sample and hold values are converted into digital outputs. This process is continuous up to all sample and hold values are converted into digital outputs. Maximum conversion time is maximum conversion time. Maximum conversion time is, here time is equal to 2 power n minus 1 into C. Where TC is called as clock time period, where n is called as number of bits. That means to reach all ones from all zeros, the counter takes 2 power n minus 1 clock pulses, where n is the number of bits. Where n is the number of bits. The disadvantage of this one is the technique is low speed is the most serious drawback of this method. Coming to this one here, initially the reset signal is active condition. At that instant, this counter at that instant that AND gate is not supply any clock pulse to binary counter. When reset is in inactive condition, the AND gate is enabled. The AND gate is allow these clock pulses which are applied to binary counter. Total for 3 bits, 2 cube is equal to 8. 8 clock pulses are required to convert that analog input into analog sampled hold value into binary or digital data. This is the clock pulses. In when that AND gate allows the clock pulses, the reset signal is in inactive condition. This is the VD. This line represents. This is the line represents VD. The output of that DAC is a staircase waveform. The output of that VS is staircase waveform. That is VD. VD is the staircase waveform. In reset is in high condition. That is means binary counter is in reset to 0. The output of that VD is 0. The output of that VD is 0. That is 0. Upon release of that reset condition, that means reset is inactive condition. The clock pulses are reached to binary counter with the help of that AND gate. For first binary, for first clock pulse, that means compare VA with VD. Compare VA with VD. VA is greater than. At that instant, this is the VA value here is higher than that VD. VD is 0. VA is at a higher level. This is the VA value. This line represents VA value. At that clock pulse 1, VA is higher than VD. VA is higher than VD. Therefore, the output of that comparator is 1, allows the clock pulse 1. And at that instant, second point, here second point, again VA is greater than, this is the VA during that period, VA is greater than At that point, VA is greater than VD. Therefore, comparator output is 1 and gate allows second clock pulse. At that instant, this is the output of the, this one is VD. This one is VA. At that instant, VA is greater than VD. Again, output of the comparator is 1, allows third clock pulse, and so on and so forth up to 8th clock pulse. At that instant, that VT just crosses the VA. VD is greater than VD is greater than or equal to VA. VD is greater than or equal to VA. VD is greater than or equal to VA. The comparator output is low, and the output of the AND gate is disabled. AND gate is disabled. It does not apply any clock pulses to the binary counter. Binary counter stops the counting. In previous case, the number of pulses counted increases with time. The number of pulses count increases with time to 8. This is the 3-bit counter type of digital to analog to digital converter. Analog to digital converter. One sample and hold value is converted into digital data. Whenever that AND gate is disabled and not apply any pulses to that binary counter stops the counting. At that instant, the output of the binary counter is stored in the latch that represents that digital output related to sampled hold value, that is 1. Okay. Next, second sample and hold value is applied to comparator. At that instant, again reset the counter. Again reset the counter by using a reset signal. The reset signal is active. The same process is repeated for all sample and hold values. For all sample and hold values. With this, the analysis is completed.